Hello, linear algebra student. This is a continuation of chapter 1.4. We're trying to figure out if we want to solve AX equal to B. In what situation will the system have solution? That means I can actually do linear combination of these three columns to get my B. So what are the possible one? And so we do have to do row operation because B1, B2, B3 are variable. So we eliminating the first two zeros to get to the row echelon form. So we are going to have 1, 0, 0, negative 3, 4, B1, and all these. So this is what we drop off in the last video. We're going to eliminate this to 0. So you can see our row 2, if I multiply by 2, so the second would be 2 of row 2 plus row 3 put into row 3 would work, right? So 2 of row 3 would be negative 14, negative 12, 6b1 plus 2b2, and row 3 would be 0, 14, 12, just like what we expect. This would all be 0. Negative 5b1 plus b3, right? So it would end up being 1, negative 3, negative 4b1, 0, negative 7, negative 6, 3b1 plus b2, and then the answer would be 0, 0, because these are all 0. So I should say come back here. So it's a little messy here. And this would be, you add this together, so it would be b1 plus 2b2 plus b3. So what would happen is these systems would have solution only if this is A0. Okay, so solution exists for if B1 plus 2 of B2 plus B3 is equal to 0. So anytime you have this AX equal to B, if your B is, for example, B equal to, okay, 1, 1, so if I have 1, 1, I would have 1 plus 2. So third is negative 3, then there is solution. If it doesn't work, then there is no solution, right? So for example, if B is 110, you can see that it become a number, so no solution. And we can check it by going to do the RREF of the augmented matrix. Where's my here? So my number was here 1, negative 3, 5, yeah, and then I'm gonna do 1, 1, negative 3, right? So REF, so you can see there is solution. It's a mini solution. But if I do 110, means B1 plus 2B2 plus B3 is obviously not 0, so there's no solution. Remember, now this E now is the augmented matrix. Okay, so get the idea. So the idea is you don't have to do, even if you don't know the other side, if in theorem 4, if there is a prefix position in every row, then you can have any solution. You can all of them will have solution. Maybe more than one, but you can always solve it. But if you don't have every prefix position in every row, sometimes you would have no solution, because that means in that row that doesn't have, you could end up have 0, 0, 0 B or 0, 0, 0, 0. So it depends. And to find out the situation, you actually have to do a elementary row operation by hand. So you do really need to know how to do it. Okay, so do this one. Another one. So I have a and a B, and I want to see if AX equal to B is there is a solution. So check if AX equal to B has solutions, right? For every single B. So by now, you know I would have to check the row echelon form of 1, 1, 0, 0, 2, 2, and negative 1, 2, 4, right? So see, did I have that? 1, 1, 0. Oh, I have it in B. Negative 1, 2, 4, right? I have it in B. I enter it in B. So I just do the echelon form of B. It is a prefix position in every row, right? So you will say just remember the theorem works for A, not augmented A. So it is 1 0 0 0 1 0 0 0 1. So this is perfect position, perfect position, perfect position, perfect position in every row. So there is no chance of no solution. There is no chance of infinite solution. So all B has solution. Probably just one solution. Okay. Determine if this three vector will span out 4. So that means out 4. That means if I am to solve 1 1 0 0 2 2 negative 1 2 4 x1 x2 x3, right? Because I have 3 column, and I would have this doesn't make sense because these 3 vectors are 3 rows only. How can they span out 4? I think there is a typo here. I am going to just say 0 because it would not span out 4, right? Because these are just 3 columns. So let's make this 0. Just make it 0 0. So, but this is 3 columns, so it's x1 3. So this would be a B, right? So we would be asking if there is a solution in every single one. So if you are to do this, so let's just enter these 1 1 0 0 to do 1 1 0. Yeah, I need to enter a. Oh, I need to enter 1 1 0. Where is it? It's over here. I enter some, but I think we need to enter a row of 0. Just pretend there is a row. So because otherwise you can't span out 4. So I have 3 vector. Can it span every single one? So let's do a B. Okay, 1 1 0. So it is B. So we only have perfect position in 3 rows only, right? So that is not possible. No. Perfect position. Oh, this is actually the same as what we have, right? In 3 rows only. So not possible. Not possible to span off for any B of x1, x2, x3, x4, right? It has to be R4 has to be x1, x2, x3, x4, b1, b2, b4. So sometimes it's okay, sometimes it's not. So this would be not possible because we only have 3 so RREF is 1 0 0 0 1 0 0 0 1 and then 0 0 0. So it's not possible. Next things is just continue with treating the matrix and vector. So if I am to multiply matrix and vector, so in the past we say if I see a AX like this, I would need to do a vector linear combination of vector 4 times the first one, 1 times the second one, 2 times this, right? So you can see that if you do that, that's actually the way we did it would be the same as so if you look at this, you would it is basically so it's basically 4 times 3 4, right? And then 1 times 1 negative 2. So by definition, this is the definition. 2 times 6 3. But if you look at how I did it, the answer would be 3 times 4 add 1 times 1 add 2 times 6. So we could actually give it a more efficient way to say, just do it right away. 3 times 4, 1 times 1, 2 times 6, right from the start. So don't do this, but do it as the whole row times the whole column. So 3 times 4 plus 1 times 1 plus 6 times 2. So it will be faster. And then for this one, the second row, the whole row times this column. 4 times 4. So that's what it is about. It's a more efficient way of doing matrix and vector calculation. Negative 2 times 1, negative 2 times 1, plus 3 times 2. And you can see that it would actually have the same answer. 12 plus 1 plus 12, so that's 25, right? And 16 minus 2, 14. 14 plus 6 is 20. So you can see it is faster than listing them out. So that's what this is about. The second one is if I am to multiply ax and ay, so this is a, the same one. I multiply by x, that means I do a linear combination of these columns by this weight, and then I do a linear combination of a1, okay, no, this is also a, but then there's another y. I can actually add them by kind of like factoring, right? So x plus y. So this is what it is. So I would actually just do 3, 4, 1, 1, negative 2, negative 1, and then I just add them together. 4 plus negative 2 is 2, 1 plus 3 is 4, and I'll just do it here. Row times column, 3 times 2 plus 1 times 4, 4 times 2 plus negative 2 times 4, 1 times 2 plus negative 1 times 4. So if you add them together, that would be 6 plus 4 is 10. 2 times 4 is 8. 8 minus 8 is 0. 2 minus 4 is negative 2. And so it's just a little faster. Whereas in the by definition, you have to put them in linear combination. It just takes too long. So this is just a quick way of doing ax and also au plus y and all those things. But it is really straightforward to understand. Okay. The most important things in this section of 1.4 is Theorem 4. Knowing that even if your B is not known, if you look at your column, if you look at your matrix A, not the augmented matrix, look at horizontally, if there's a prefix position in every row, then you can solve, you can have solution no matter what. You always have solution. Okay, you would not have a 0, 0, 0 because reduced row echelon form guarantee that you will have some solution. If it is not, if you don't have prefix position in every row, then you might sometimes have no solution, sometimes you have solution. To find them, you have to do elementary row operation. So make sure that you master these. The question, like this question and these questions, these two questions are doing manual calculation, that is important.